We now turn to a very important topic, the technique responsible for training neural networks. Here I will get more into the details rather than just having a high-level overview. So I will not shy away from the mathematical formulations, and I believe it's a way to have a proper understanding of what is going on. This might be bad news for people who don't like equations, but my advice, don't feel intimidated and keep your eye on the big picture. We will always be connected to the intuition, and I tend to rely a lot on visuals to make the job easier. Now let's get straight to the point. So what we want to do here we have a network of L layers, and we have a cost function that measures the deviation between the network output and the expected output. This is a network output, which is y hat, and this is expected output. This comes from the label from the dataset. This y is expected output. So if you check the previous tutorial, you know that when we create the network, we initialize the weights of the network randomly. So all these weights were initialized randomly rather than having proper values. So there is no reason for us to think that these random values will create y hat close to y. It only happens after the training, and the training job is to replace those random weights with proper weights. That minimizes the distance between y and y hat. But as long as we have proper labels and we have a way of measuring the deviation from the proper labels, then we can push the network weights to minimize this cost function or the deviation. The concrete question then is, which weights give us the lowest error? Let's look inside the network and try to answer this question step by step. So here is a recap of the perceptron before moving into the neuron. In the perceptron, we are doing two main operations. The first one, as you can see, is just weighted sum of the inputs. So this part, we're just multiplying each weight by the corresponding input and summing the results. Then the weighted sum is tested again as a threshold function. If it's greater than a specific threshold, then the output is 1. Otherwise, it's 0. Now, how is this different from the neurons? In the neural network, we have perceptron-like units called neurons. I'm saying perceptron-like because they are pretty much the same, except that we replace the step function with a differentiable activation, something like a sigmoid. This crucial difference is one of the technical requirements of the gradient-based function minimization, as we will see. Now, when the input goes in, all the neurons are applied in sequence according to the layers order, and we finally have some output, like this one. The output is, of course, not what you want, because you pick the weights, as you remember, randomly. But it's a good starting point, because we will use a technique that allows us to start somewhere, even the random weights, and then gradually get closer to the target weight, a technique called gradient descent. And here is how this happens. We will use the error function here to answer a very natural question. How does a small change in the network weights and the biases affect the error function? In other words, if I make a small change in this parameter here, so this W, how this is going to impact the cost here? So if the weight is increasing or decreasing, will the cost function increase and or decrease, and by how much? This information will allow us to move faster in the direction that minimizes the error function. Now let's be more formal. Let's focus on specific weight value here and the relationship with the cost function. Imagine that this line is a line that represents possible values for the particular weight we choose. And for each value, we have a corresponding cost or error. So for example, if you have a weight value here, you might have the corresponding cost like here. And this one, the corresponding cost is this. And for this one is this, okay? Now, let's assume that you already have a function for all possible weight values, something like this. Since your goal is to achieve the lowest error, your target is to find the weight here. But you did eyeballing to get this weight value, and it's not possible to do this in practice because we just assume that we know the cost for all possible weight values. But we will use a simple technique that can scale, and it relies on the gradient information. And here is how it works. Let's assume that your random initialization landed you here. So you have this particular weight value and this corresponding cost value. And you're trying to find your way towards the minimum, which is this. And you ask yourself a question. If I change W in this direction, if I have delta W in this direction, what is the corresponding change in the cost? And the answer is this, that the cost will go down, so the change in the cost will be negative. But if you change W in this direction, you know that this is a corresponding change in cost, and this means that your cost value is increasing. So since your goal is to minimize the error, it's very clear that you want to follow this direction here, because it's the direction that minimizes the error or the cost. What we just did is calculating the gradient of the cost with respect to the weight. And we want to find the weight value that makes this quantity negative. So in other words, we need to change the weight. Say we have initial weights as W. We need to change this to W plus delta W. But what is delta W? You're going to choose delta W to be the negative of the gradient of the cost with respect to the weight. And you continue to do this repeatedly until we hopefully reach a global minimum. So the first step might take you to this direction, and you get to this point. You make another move, you get to this point, and finally you get to this point. The question is, how do we get this quantity? How do we compute it? And this is what we are going to do in the next few slides. So the rest of the video is about answering this question, but here is the big picture. To make things more tractable, I will take a snapshot of the network. So here I'm highlighting the following neurons path, and I will set the mathematical notations that we will follow. So you recall that each neuron is just two operations, the weighted sum of the inputs and the nonlinear activation. And we will call the output of the weighted sum as Z, and the activation as A. So we can visualize each neuron as just a split circle, and the left half is Z and the right half is A. But since we have multiple neurons in each single layer and we have multiple layers in the network, we have to extend our notation, which is why we will be using the superscript L for layer and the subscript J for the perceptron. And for example, here we have a perceptron or a neuron in the last layer. The last layer is referred to as L, capital L. So the neuron has two components, ZLJ and ALJ. And now the last thing to be considered is setting some notation for the weight. The weight notation is slightly tricky because the weight is between two neurons. But again, the superscript is for the layer, but it's about the ingoing layer. So this particular weight has a value of L, which means it's ingoing into another neuron in layer L. The subscript has two symbols. The first one is the index of the ingoing neuron, while the second one is the index of the outgoing neuron. This can be counterintuitive, as one might expect the order to be the other way around, but it's done for mathematical convenience. Let's revisit the neuron through this notation. So the neuron activation is just sigma applied on the Z quantity. And what is it? It is the sum of all neurons from the previous layer. And each of them is weighted by W ingoing into the current layer and connecting the current neuron with all the neurons in the previous layer. Great. Now let's go back to our snapshot and try to compute the error of the last layer, this quantity. But let me remind you of the big picture in case that notation discussion got you distracted. We have an output from a randomly initialized network, this y hat, and we measure the distance between the output and the desired output using this cost function c. We want to use this total error to adapt the weight in the network, each single weight in the network. So this means we want to calculate the gradient of c with respect to each weight in the network. I call this quantity the error. So let's look at this particular weight. So you know that any change in this weight will cause a change in z, which in turn will make a change in a, and finally will influence the cost function. So if you want to compute the error for this particular weight, it makes sense to look into the error for z, and from it you can derive the error for the weight. But how do you calculate the error for z? Well, we don't know, but we are going to use the same strategy, which means we are going to calculate the error for the activation, and from it we use it to calculate the error for z. Let's apply it to the case here, and I have this small figure that will help us in this job. So the error of the last layer, which is the gradient of the cost with respect to the z quantity. So what I'm going to do is, instead of calculating it directly, I'm just going to multiply the gradient of the cost with respect to the last activation. It will be multiplied with the gradient of the last activation with respect to the gradient of z quantity. So this intuition is in fact an application of the chain rule in calculus, something you are probably very familiar with, and we are going to use this trick all the time. That's why many people say that backpropagation is just an application of the chain rule. So the equation for the last layer is the one I'm showing here. The first term depends on the choice of the cost function. We didn't specify what will be the cost function yet. And the second is a gradient of the activation with respect to z. And it follows simply from the definition of the neuron. We can easily calculate this quantity here. I included the notation here for the neuron as a reminder. And from it you can see that the second term will be simply the derivative of sigma of zl. This equation is very easy to calculate. So for example, if you have your sigma as a sigmoid function, the derivative in this case will be just the sigmoid of z multiplied by 1 minus sigmoid of z. And for example, if the cost function is the square distance, then the derivative of the cost with respect to the activation will be just y hat minus y. And it is very easy to multiply those quantities to get the error for the last layer. And this leads us to the first equation of backpropagation, the one responsible for calculating the error for the last layer. But what about other layers? I want to calculate this quantity for other layers as well. So now we want to calculate the error with respect to z here, but the connection between z here and the cost is a bit more involved. So unlike the last time, the change in z will have a change in the activation, which will result in a change in multiple neurons in the next layer rather than one, and they in turn change or influence the cost. So again, we will play the chain rule game, except this time we're going to do it multiple times. So we need to calculate the gradient of this multiplied by the gradient of this, and we need to do it multiple times. This is the equation for it. It is the sum of these gradient multiplied by those. Again, we have two terms in the sum, but we have a nice thing here. So if you look closely, you know that we have already calculated this quantity. It is the error of the next layer. And so we take the stored value of this error and multiply it by this quantity. But the question here is, what is this gradient? How do I calculate it? Again, I will be using the neuron definition. So this is just the weighted sum of the previous layer activations, including this one. And we know that the other activations are irrelevant to the gradient calculation, so we will need to compute the gradient of this term based only on this value. and it is just the weight multiplied by the derivative of the activation. This here. And this is the second equation for backpropagation. So combined with the first one, we can calculate the error of each single layer in the network. And we are just one step away from getting to our target, calculating the error for weight. But let's take a moment to appreciate this equation. So it allows us to calculate the error of the last layer from the error in the next layer. In other words, it allows us to backpropagate the error. So given the error in the last layer, you can compute the preceding layer error and so on until you reach the first layer. Now we will turn to the weights, and I will take this weight here as an example. So again, we will play the general game, and we will get the gradient by multiplying this quantity by this quantity. And if you remember, we have already one of the two terms calculated for us. This one, because it's a layer error. And the other term, this one, is equivalent to the activation of the neuron. We can easily check this from the neuron equation included here. And here is the final equation for the backpropagation. So a quick note here is that the bias error is just a special case of the weight error, because in the original equation I have assumed that W0 is equal to the bias with X0 is equal to 1. And so you can calculate the error for the bias easily as just a slight modification of this equation. So feel free to give it a try yourself. Now let's recap before finalizing the backpropagation algorithm. So we have three equations. One that gives us the error for the output layer, and from it we do a backpropagation to calculate the error for other layers. And we can use the first two equations to calculate the error for the weights, which is a gradient of the cost function with respect to the weights. By the way, you can easily convert this into vector or matrix notation, and we are going to use something like the dot product or the element-wise multiplications. These are more convenient to implement using libraries like NumPy in case you are thinking about implementing this yourself. And here is the final algorithm. So for each training example, we have the data itself and we have the corresponding label. We perform a forward pass, which means we are applying the neurons in each layer in sequence on the input example to get a prediction. Then we calculate the last layer error using backpropagation 1 equation. And from it, you can calculate the error to the other layers using backpropagation 2. And finally, you calculate the weights error. You use the weights error, use a gradient of the cost with respect to weights to update the weights value and get the new weights using gradient descent. And then you perform this repeatedly until you converge. Thank you.